Good morning. My name is Gregg Lippa. I work with for themisinc.com or for Themis Inc. And here's our website, recently redesigned. This is our page for webinars. And as you can see, new features of Java 8 with me has a little button here. You can get the slides. So that's themisinc.com/webinar, or just use the menu at the top and pick webinars, and that will allow you to get a copy of the slides which have been published. I made a couple of last-minute changes, so hopefully they made it up there. If they didn't, they're pretty minor. Again, my name is Gregg Lippa. I've been with Themis for about 9 years. I've been working with Java for close to 20 years prior to that, and still involved in the mainframe world, although that doesn't relate to this topic. That's my background, all things Java. And this presentation is about Java 8 new features. Java 8's been out there for a few years, but the new features are something that a lot of people are just beginning to embrace and use. There's lots of little things and a few very big things. So in this webinar, we are going to discuss some of the main things that Java 8 has added, including things like Lambda expressions. Let's see if I can. Lambda expressions are a whole new thing. Unless you've worked with them in some other language, they're very different than anything you've seen before. The ability to use code as an argument. Code is now a thing you can pass around, something new in Java. Interfaces have changed a bit. We now, in addition to functional interfaces, we have other capabilities like default and static methods in an interface. The collections framework has changed substantially with the addition of streams. Streams allow you to do almost SQL-like processing on the data in a collection or some other source of data. The date-time approaches to how you organize date and time data has changed for the better and substantially, not since version 1.17, when calendar was introduced, has there been substantial change to the date time, and now it's really quite the overhaul. The optional class has been added. It's a different way of managing nulls rather than lots of null pointer exceptions or constantly testing to make sure you're getting a data instead of a null. The optional class gives you a new way to handle that. Minor changes to JDBC, won't spend much time there. It's going to be a pretty full period. There are places for you to put your questions, but I respectfully request that you send your questions to me at my Themis email, and I'll be glad to follow up with you after the webinar. So what is new? This is lots of new features, but the ones we're going to focus on, the significant ones, first of all, interfaces, this ability to have two new things in an interface, a default method and a static method, both ways of actually putting implementation code into an interface. We never had that before, and now we do in a couple of different ways. We also have the notion of a functional interface. We've had those in practice, but now they're a thing. A functional interface has a single abstract method, and that's very important, particularly in this new realm of lambdas and lambda expressions, which rely on the notion of a functional interface with a single abstract method. Method references themselves now, like I said, they can be passed around and stored and used as a type. We'll talk about that. Another big change has to do with the stream API, not the I/O streams that you're used to from reading files and writing files, but the stream API that works with collections and allows you to process your collections and sort and filter and map and do lots of things very similar to what the capabilities are of an SQL statement. Like I said, the datetime API has gone through quite an overhaul, including immutability and thread safety. So we now have type safety and thread safety, but lots of additional functionality. Optional, I mentioned. We'll look at that in some detail briefly. The ability of JavaScript to run much more effectively. There's a new JavaScript engine that has replaced the aging predecessor. So you can invoke JavaScript from Java, and a variety of new tools that we won't really spend a whole lot of time on, but JDeps is mentioned here as a tool that looks at the dependencies among your Java classes. So let's just review for a moment what is a Java interface. Prior to Java 8, it was a way to separate your design from your implementation and have a type play different roles in different contexts. Prior to Java 8, all the methods were abstract and had to be implemented by a concrete class. That is what's demonstrated down below, where we have a little interface called purchasable with a couple of getter methods that make it up, and a class called item that implements purchasable and provides implementation code for those two methods. That's pre-Java 8, so that's the baseline that we begin talking about what's new in Java 8, which, first of all, we have default methods. We have the ability to provide an implementation for a method right in the interface. Concrete method implementation in the interface itself, so that the classes that implement those interfaces do not need to override them. They can, but they don't have to. So here we've updated our purchasable to define this default method, getShipper. So by default, we use the United States Postal Service as our shipper, and if you ask anything that implements purchasable to do a getShipper, it can do this. Alternatively, we could override getShipper and say, no, we're going to be using UPS or FedEx or whatever, but you don't have to. So default, you can have as many default implementations you can have a default implementation for as many methods as you like. And what this would do is allow you to have a common implementation that's reusable. An example is mentioned here that in Java 8, iterable has a default method for each, which we're not going to get into, but it now supports the ability to provide some processing mechanism in a more automated fashion. So anything that implements iterable, and there are many things that do, can take advantage of that for each method. We can add new methods to existing interfaces without having to go change the code on the implementing classes. If those new methods that we add to the interface have a default implementation, then it won't break the code in all the implementing classes. So that's another benefit. If you've been around Java for a while, you know that the adapter pattern is pretty common, and we often have interfaces that require adapters just to take care of methods that we don't really need to use out of that interface, providing often empty implementations. That the need for that has been reduced with the default method capabilities. And many enhancements to the collections API, including those that support Lambda expressions, make use of the default method capabilities. So we'll get to Lambdas in a minute. The other capability, static methods, take it even really a step further. You still have the ability in Java 8 to have implementation code in an interface, something we never had before. But now these static methods can be called without even an implementing class. So now we have our purchasable interface, still has the default method, that we just talked about, but now has a new static method added to it called getShipOptions. And it does work. It's not intended, can't be overridden, just like a static method in a class doesn't get overridden. But here, the shipping options, the big 3 shipping options, are returned in an array of strings from the getShipOptions. And down in this little main method, all we do is call purchasable.getShipOptions. Being static means we can just refer to the interface name, same way we referred to a class name prior to Java 8. So now with static methods, we can make an interface a utility holder, holder of utility methods, and not have to put those in a class. It's an option that we have. And following the same rules, they cannot be overridden by any sub-interface or implementer of that interface. And you'll find that comparator, which is so important for sorting, has a number of static methods that have been added. If you look into the API, and this reduces the need for a separate factory class to support different comparator implementations. So that's a look, first look anyway, at how interfaces have changed. The notion of a functional interface is critical for a number of the other enhancements to Java 8. A functional interface simply has a single abstract method. We've already had, again, in practice, a number of functional interfaces. Runnable has the run method, comparator, the compare to, clonable has the clone. Single abstract method. This is not a limitation in terms of what we just discussed with default and static methods. You can have as many of those methods as you'd like, but only one abstract method, and this is where Lambda expressions come into play and are required. Now, if your functional interface overrides any of the toString, equals, hash code types of methods from object, those do not count towards your limit of one abstract method. So you can't have too few or too many. And you can annotate it, kind of like override annotated things since Java 5 to tell the compiler to do a check. Functional interface does the same kind of thing. Calculable in this example would still be an abstract, would still be a functional interface even without the annotation to say it is. It is as long as it has the single abstract method. In this case, getTotal is our abstract method. It does have a static method, getValidOperators, something that's calculable, allows you to pass in to getTotal an operator and 2 numbers, and it does the math. And the valid operators are listed here so that a caller can find out what 5 operations are supported by an object that supports the calculable interface. So it may seem fairly simple, but it's the real underlying capability that these Lambda expressions depend on, and we'll see that coming up shortly. These are often referred to as certain acronyms that identify them as a single method or a single abstract method type of interface. Other names for the same thing, they're called functional interfaces. And finally, we get into the Lambda expressions we pointed to a few times over the last 15 minutes. What are they? What good are they? What requirements do they support? How do I do it? What's the syntax? And what about these method references? What does that even mean? And how do I use them? And how do I call methods that will accept Lambda expressions? So that's what we need to look at over the next 10 minutes or so. In the end, you're going to have simplified code. In the interim, you're going to have a concept that may tax your brain a little bit and certainly change the way we see Java syntax. So it is Java 8 that introduces these lambdas, which is a block of code. Here we have our definition. That can be a block of code that can be referenced and passed to other code and then executed in the future as many times as you need to. Technically, they are anonymous functions. They accept arguments, they return values, and they can throw exceptions. So they are functions or methods. Now here's a simple example. Here we have a comparator of integers. So our class is called integer sorter. It implements comparator of integer. It overrides the compare method by simply subtracting the second number from the first number. So this is something that would have operated and worked the same way since Java 5 or Java 2 comparator. That's what you know, or most of you know coming into this. The equivalent lambda expression is shown down below. And the pieces are kind of spelled out for you. What you have is a parenthesized parameter list, integer I1, integer I2. The new syntax, the lambda arrow, dash greater than, and then the implementation code, in this case the very simple implementation code with the implied return. So this code, return I1 minus I2, implies the return keyword and returns the result of subtracting those numbers. So this is your first look at a lambda expression today. The implementation code says, take these two arguments and make it so that the second one is subtracted from the first, and we return the result of that. And that's, of course, how the comparator figures out how to sort, what order those numbers are going to be sorted in. Excuse me. So here are a few examples of the comparator being used the old-fashioned way, where we just instantiate integer sorter, which was on the previous slide. Integer sorter is the code we saw there, and assign that to a variable called comparator and use it. With the lambda expression, we can have that inline, or we can have it referenced by a variable. So inline, what we've done is taken this code up above and changed it. Instead of referring to this new integer sorter, we have placed the lambda expression right in line. So this is the implementation of the compare method that's required. The sort method requires that if there is a second argument, it implements comparator. And that's what this does. It implements an appropriate comparator. Since we have a list of integer, this comparator would have to be a compare method that takes integers. Now what you're seeing is that same lambda expression. These are the same expressions. Instead of being fed directly into the sort method, it's being assigned to a variable comparator that references a comparator of integer. And now we could reuse this variable if we wanted to sort a variety of lists of integers. We could use it by name. So again, there's a similarity between the lambda expressions being the same. There's also a similarity here where we instantiate an integer sorter, which is a whole separate class that we had to write to support integer sort or integer compares, or we can just put in the meat. It's basically a matter of subtracting one integer from the other. So what lambdas do is implement a functional interface. The reason that we get to leave out so much of the detail is because the interface has defined a single function. The interface has a single function. So we saw how integer sorter implemented comparator, implemented the compare method, and that's how Java knows how to interpret that lambda. There has to be a functional interface where there's exactly one abstract method, and the lambdas are treated as an implementation of that interface. So as long as a method is expecting an argument, and that argument type refers to a functional interface, then you can use a lambda expression and thereby avoid writing an entire class just to implement that one method. You can pass the implementation code directly. As we saw, behind the scenes, a class is actually created and instantiated. But it simplifies your code. Here are a few other examples. Here's our functional interface, nice and small. It's called MathOp. And you see how we've declared 4 variables that reference that interface. It's a functional interface, not because it says it is, but because it has a single abstract method, calculate. Now, what we're demonstrating on this slide is a variety of ways that you can code that lambda expression. You can explicitly specify the types of the arguments or not. They can be inferred. MathOp already knows what types those arguments are, so you could leave them off or put them in for better documentation. The third example shows braces and a return statement. The return is implied. A plus B, A minus B implies that that's what will be returned, is that value, but you can use braces to supply an entire code block. And this is a code block of 1 line. So we certainly didn't need the brace return. But if you are going to code multiple lines of code, you will have semicolon separators or semicolon statement terminators. And the fourth and final example here shows multiple statements. They are strung across a single line, so everything fits nicely on the slide, but the braces here would be required because we have multiple things happening. In other words, for division, we're going to do the work of checking the denominator before we divide. So if B is 0, we're just going to return 0. Otherwise, we're going to return the result of A divided by B. And in the output, we've done division both ways so that we can see, the 2 results. But what's happening down here is the calc method is being called. This is a class called Lambda test, and we create an instance called testme. And then we call the calc method of testme 5 times down here. And the calc method says, well, give me the numbers and give me a MathOp that will define what kind of calculation we're doing. So add, sub, mult, and div are the variables that were defined here with the proper type of MathOp, and those are being passed in as the third argument. And then the calculate method is being called. So a MathOp is a functional interface. It has the one method, calculate. That method requires 2 integers. A and B are being passed in as the 2 integers. And what exactly happens to A and B is defined by the lambda expression in the MathOp. So that's mult. It's a whirlwind tour of some pretty hefty concepts. One last thing on lambdas before we switch gears and talk about the Stream API, are method references. So another new bit of syntax here. We can make this look like a button. we have a double colon syntax that allows you to refer to methods in this kind of a syntax. You can refer to methods by their name and their container. And you can do this with static methods, instance methods, and constructors as well. For a static method, you would use the class name. So here our class name is mrtest. Our static method is compareStrings, and we're calling mrtest.compareStrings this way, but we're using the approach of the method reference that's new in Java 8 this way. With instance methods, we don't have an example here, but you would, of course, create an instance and call the method that way. With the constructor call, you would use the new method, the keyword new, along with the class name. So constructors are themselves somewhat static. New is the way that you call a constructor. So when we call mrtest here, we're actually using a Lambda expression. So we have this list of strings called names. We're telling it to sort, and we're passing it a comparator, or it requires a comparator as the argument, and our comparator is this method down here. compareStrings implements compare to on the two strings that are passed to it. And what you're seeing with the method reference is that compareStrings is being called without the argument list. The arguments are being implied. So the two string arguments are being used by that method to sort out the list of names by comparing them to one another and putting them in alphabetical order. So you have yet another even more simplified reference than the Lambda expression that could be useful in certain scenarios. Okay, next topic, we have the Stream API, which really takes advantage of what collections have been doing for us for years, which is being containers of data, but fairly limited containers. You know, they didn't have the ability to do a lot of things very easily without writing a bunch of code, including things like grouping and aggregating, but even simplifying things like filtering and sorting. And what we now have is basically a declarative approach to working with a collection and doing the things that that collection needs to do. We have the Lambda syntax and method references coming into play to help out with this. Now this will remind you of SQL. It does many of the same kinds of things that we do in a where clause or an order by or a group by or even the select line, where we map a row to a set of columns that we're interested in. What a stream is a series of operations on a sequence of elements. So what we do is we tell the collection that we need to get a stream. And on that stream, which we obtain from the collection, we can do as many or as few intermediate operations as we'd like, chained together in a pipeline format that you see kind of in the picture down at the bottom. So we obtain the set of values that we're interested in. We apply filters to them to obtain just the ones that we want and eliminate the ones we don't want. Multiple filters perhaps. We sort those based on some characteristic of the objects in the collection. We then possibly map them. So rather than getting a whole object, we may get a subset object or even create a newer object to support that. And then in the end, we collect those values into a new collection that gets returned. So that's a terminal operation, the one that puts together the final collection. Here we have a series of intermediate operations that do things like filter, sort, and map. And we start the whole process off by obtaining a stream from our collection. So let's take a look at an example. At the left-hand side, we have no stream test. On the right, we have stream test. And the goal is to return, we have these items you can see down here where we're instantiating items. They have an ID, a name, and a price. So the adapter costs $20 and the battery costs $10. And we are going to take this list of items that we get down here, get all items. Either way, get all items calls the same method. So we're going to get a set of these 4 items in an array list. And the old way, without streams, we would go through, we're trying to get the ones that meet this filter, cost less than $50, are ordered in this way, descending by price, and we only want the IDs. We don't want the whole item. So we're going to map from a whole item to just an ID. Those are the 3 things we're doing. First, we're filtering, price less than 50. So we process the list this way. For each item, if it's less than 50, add it to this interim list. Then we're going to sort. So we're going to take that interim list and sort it using a comparator that compares the price. So we're going to compare each pair of items based on their price. So this blob of code does the sort part. This part does the filter part, and we had to have an interim list to work through those. And then the mapping part is to return just the IDs of those items. So here we have a new list, not a list of item, but a list of integer, because the ID of the item is an integer. So we're going to populate our final list of IDs with just the ID of the item. So we're going to walk through that interim list that we built by filtering and sorting. We're going to walk through that and just add the IDs to this list, and then ultimately work with that list. Now, part of what the intent of this slide is to do, we have the blue box outlining these 10 or 15 lines of code that did the work the old way, and comparing it to the stream way of handling the same problem in 5 lines. You know, much more simplified code. So how do we do that? Well, we got the list of items the same way, right? We have this get all items and we get a list. So those 2 lines are identical. It's really all this processing of what we do with those items, the old way versus the new way, where we say, stream those babies. I need to work through the items. How? Dot filter. So a stream has these methods, dot filter, dot sorted, dot map, dot collect, many more methods like it. So get me a stream, and you notice that we've chained all these together into a pipeline. Here's the semicolon. This is one statement. So get the stream. Using that stream that you just got, filter. And what do we have here? Lo and behold, it's a Lambda expression. Filter by checking that the price of the item is below 50. Then take that collection that results from removing all the expensive items, like the printer, and sort that. And here we have a method called comparing, and we're using item get price and reversed. What is going on here? Well, comparator has some static methods. New in version 8, we have static methods. One is called comparing, one is called reversed. So the imports are not shown. We'll show you a few imports later on, but import static, Java util comparator.asterisk will get you the ability to short circuit references to these two methods like you see here. So the comparing is being fed the getPrice method. In other words, we want to sort by price, and the reversed gives us the descending part. Because if we just do comparing getPrice, we'll have an ascending order, but here we're going to just reverse that. So we have all these calls. We're taking items and getting a stream from it, and filtering that stream, and sorting that stream, and reversing the sorted order, and then mapping. So now what we have is a sorted list of items, but we only want the ID. So the method that we're using to do the mapping is getID. And we're going to collect together all those IDs to create a new list. And then we can just print that out. Either way we run it, we're going to get the list of IDs. Remember, we didn't sort by ID, we sorted by price. So 234 has the highest price, 40. 123 has the next highest price, and 345 has the lowest price, and 456 is not on the list because it got filtered out. All right, so if you haven't seen this before, it's got to be a little bit daunting to look at, and this is a fairly simple, though somewhat complete example of how the whole thing works and how it compares to the way we used to do things. Much, much more to it, just to kind of give you a sense of how complex this stuff can get. We put in a little piece of the API doc for the grouping by method, and you see some, triply nested generics being used. I certainly don't want to go through and try to explain this, but you can see that there's some new classes. We'll talk about function a little bit more. Lots of collector is also new, but lots of pretty complex stuff going on here. So yeah, this is not something you're going to pick up in an hour or a day. It's something you're going to have to work with. Hopefully, maybe get a little training on. Lots of new functional interfaces. We mentioned a few here, and they come in families. There's a predicate family, double predicate, in predicate, various types of predicate itself. Comparator and function are also functional interfaces that have important roles to play in the streaming. There are consumers and suppliers that have been added to the Java 8 API, and those are able, for instance, a consumer can be set up to process each element of the stream and gets called on each element during the processing. So there is much more to streams, and that's just one more page, still more. Filter and sorted we saw, and very similar to, again, SQL. We have the ability to trim things down, removing duplicates, skipping over the first few, or limiting ourselves to a certain number. We have a whole family of map capabilities to transform the stream, like we saw from an item to an integer or to some other type. And again, that reminds me a little bit of XML style sheet, XSLTs, that transform XML documents into other things. We have a variety of collection capabilities that produce the output as we saw. We did a toList to return that array list. Some of the terminal operations, the ones that actually complete the process, are reduction operations that return a single value along the lines, again, of SQL. Min, max, count, sum, average, all built-in aggregate functions we're used to seeing from database interaction. And other terminal operations that instead of producing a result, do some processing on each element. So these terminal operations for each, for instance, or for each order, receive an argument of the type consumer, which defines what you want to do to each of the elements in the stream. And still more. There's existence checking. There are other statistics you can get. We didn't look at grouping, ways of partitioning, and a big area, really, multi-threading, where you saw in that initial example that we did dot stream. You have another option here to do parallel stream, and that gives you automated multi-threading and options that will allow you to support voluminous operations using multiple cores. So streams are big. Lambdas are pretty big. I'd say streams are maybe a little bigger. They're both, you know, good size. Todd says, where does item in filter come from? They are defined, let's go back here. In the filter, what we're doing is, I think you picked up, oh, okay. Remember, items here is a list of item. So when we say filter item, we're saying that we're defining the argument to the filter method, or sorry, to the get price method as coming from the next in this list or now stream of items that are coming in. So good point. Okay, I got a couple of other sizable topics here in my hour, and then a couple of quick ones. Date and time, been there since day one with the date class, which is also a time in a millisecond, and then its replacement class, we might say calendar, in version 1.18, many years ago, back in the last century, was intended to replace calendar, which of course it did not. Date has been deprecated now for close to 20 years, but there are a variety of other problems, including type safety and thread safety not being part of it due to their mutability. Date format only working with date, so you have to extract the date out of a calendar to do formatting. Having a month index at 0, all kinds of fun things that we had to deal with in Java prior to Java 8. What happens in Java 8 is a set of 5 packages, java.time and a variety of other sub-packages that come with it that give us a whole new API, all new classes, all immutable, which helps to give us the thread safety as well. Joda time, which you can find out more about on joda.org, has been around prior to Java 8 and was the basis for this approach to new approach to dates and times. So some of the classes, there's many classes out there, your basics, local date, local time, local date time, you have kind of your date time and timestamp separated out, and a variety of others. You also have periods of time, durations if they're based on time, periods if they're based on a date range or a date extent. You have a point in time called an instant, and you also have clock, which can return the current instant. You have, of course, support for time zones. You have a variety of helper utility methods, static methods, and temporal adjusters that do things like finding the first or last day of the month and many other things. And you have a formatter. So we had date format going back to Java 1. We have date time formatter coming out of one of the sub packages of Java time for formatting. So let's look at an example, a simple example. This time we showed you some imports, including a couple of static ones format style and datetime formatter are used down here. And we put the format, the imports in. So up here, what you see is a factory method called now being called on each of the three local date, local time, and local date time to produce those three variables: today, right now, and then TS for maybe timestamp. And we produce some output from those three. So we have get day of the week. Today, I set this up to be about now, 12:15. Even down here, I got it. I had 12:15 somewhere. Maybe it's later. So get hour, it's 12. Get year, 2017. Get month, 3. Get that's the value, 1 through 12, and then get month gets you the string. So now is a factory method we see used up here. Of is another factory method that allows you to supply year, month, and day. And there is a month class. You see the import for that up here that has, of course, a bunch of constants defined in it for the months. So here we have January 20th of 2020, a date we can all hope for. And then we also take the local date here and a local time example here, 8:30 in the morning, and something around this time, 12:15 in the afternoon. And then we look at the local date time factory method of taking a local date and a local time, or of taking a variety of year, month, day, hour, minute, second, or taking a string in an appropriate format and parsing that to produce, and again, of and parse, as well as now, are all factory methods that produce an instance of a local date time or a local date or a local time. And here we're demonstrating a little bit of formatting on these lines. So we're taking a date, which was set here to January 20th of 2020, and displaying or converting that to a long form. That's what gives us January 20, 2020. We're taking the time, sometime, which was set here to 12:15 in the afternoon, and giving that a short form. It's 12:15 space PM, and then formatting TS2, which is our current, or actually November 19th, 2019 at 2:45 in the afternoon, and formatting that with a medium. So long, short, and medium are format styles, long, short, and medium. And the format, the of localized date, of localized time, of localized date time, those are methods of the datetime formatter. So those are all, taking advantage of the static import that was introduced in Java 5. And then we just print that stuff out down here with a tab separator between the formatted date and the formatted time, and the formatted timestamp on a separate line, November 19th. One other thing about dates and times is the features that allow you to adjust those values. You can do it directly using things like with year, or you can do it through math using things like plus months, or even minus. You don't have to use negative numbers, you can say minus. And I mentioned temporal adjusters. There are a bunch of static methods in there, like first day of the month, last day of the month. You also have the ability to use durations for times and periods for dates to create a span of time or find the difference between 2 points in time, an interval. So in this example, we're using a period, which is a date duration, and saying we want a period of 2 years plus 6 months minus 4 days, a little under 2.5 years. And now we can use the plus method. So we go and take local date.now, that gives us today's date, and we add the 2.5 years minus 4 days to it. We also have time zone awareness support. Let's take a look at another set of examples. Here we've got a couple of static imports that are shown. We go ahead and get a clock value for the current point in time today, March 8th, 2017, and we say with year 2018. And then we say with day of month 1, so the 8 changes to a 1, with last day of month, with next Monday, next Monday. How did I get a 2 here? It looks like a typo. Sorry about that. That would have been, should have been 313, right? 10, 12, 13, yeah, there should be a 3. Plus months 2, these are all based on today. So even though we seem to be building, we're actually just creating a new instance for each. Remember, these are immutable. So when you say with year 2018, you're not changing today. You're getting a new local date with that value. So today being March 8th plus 2 months would be May 8th. Today being 2017 minus 2 years. A little bit about time zones. I used Cuba and Japan because they were nice short names that would fit nicely on the slide. So here there is a zone ID with a variable z Cuba that references it. Again, we have these factory methods that says build me a zone ID object based on Cuba, and we get that. And then here I use the now factory method of a zoned date time, pass it the time zone of Cuba, and then when I print that out, z now is Cuba's in Eastern time, just like we are. So that doesn't change. And then here now uses the system default time zone, and Tokyo now uses the zone ID of Japan. So instead of creating a zone ID object into a variable or instantiating one, we just pass it right in as the second method, which clearly requires a zone ID instance to get Japan time. And lastly, down here in date times, go get now, go create a date of this coming Christmas, and then do a between period. Static method between today and Christmas gives us this kind of an output, 9 months and 17 days till Christmas. So get your shopping started now. The show all method is being used to display all these. It's just a bunch of display statements that would produce, you know, all this kind of output, so they're not shown. All right, a smattering of examples of how date and time work and all the things that they can do. Those are my big topics. Optional is medium-sized topics, perhaps. Checking null values instead of you know, actually containing you know, a variable that may contain null. You basically wrap your nullable variable inside of the optional instance. Optional is, of course, generic, so it supports any type. And once you have an optional instance, you can ask it, do you have a value? And if it does, you can do a get, and the get will return the value. If you don't have a value, then it will throw an exception. So it too has these kind of factory methods, optional of, some variable that are, some instance reference, or of nullable. If you're not sure if this instance reference is null, and you want to allow it to be null, then this will support that. And then you also have or else, which says, well, I'd like the value in this optional. These two are static methods. These are more like factory methods, but this is an instance method. So you have your optional instance dot or else, and you're basically saying get me the value in it, but if it's null, this will be the default value that I'll want instead. So you can provide a default somewhat automatically. It has a variety of methods that support the streaming process that we talked about. I'm not going to get into those in the interest of time. And it has other processing capabilities. When nulls are present, you can say, or else get me the value that this supplier produces, or else throw the exception that this supplier produces. And those are other ways of getting at the value. So again, we have a set of code examples in optional test. We have D1, which is null, and D2, which is not. So for D1, we do an of nullable, and OD1, which is this type, an optional of double, is going to get a null. And we do just the plain old of on D2. So this reference is going to reference an actual value. And then if we multiply those together, this is the multiply method being called, we have to pass in the two optionals. And what the multiply method is demonstrating is, first of all, call to is present, which produces this output. The first argument is present is false because it's null. Second argument is present is true because it has value. And then we actually do the work saying for val1, get what's in arg1. Remember, that's null. And if it is null or else, get a 1. And val2, we just did a plain old get. So we got the 123.45. And when we multiply those together, 1 times anything, of course, gives you that same thing. So really just more demonstration of the capabilities. Just a couple of minutes left. We have database capabilities. Not a lot of change there. There's a new type for referencing cursors that are returned by procedures typically, an enumeration of types called JDBC type, new capability for database vendors to have their own specific types. In DB2 we have user-defined types. For update counts, when you do an execute update, you get back an int. Only allows you to update 2 billion rows. If that ain't enough for you, we now have execute large update, so you can get back more detailed. Database metadata changed a little. The ODBC bridge is gone. And JavaScript, I have about 1 minute remaining. JavaScript is now supported. Nashorn is the new engine replacing Rhino, way better performance. Some of the reasons you might do this, probably not very typical in most environments, but here's an example. Anybody that's ever used JavaScript, we get the engine through a factory method, and then we're able to evaluate Nashorn eval. We define a function, we evaluate, we call the function, and we're able to see output in the Java program based on JavaScript work that was done. So you have that capability now. We do have JA1090. We have a link here to our course that covers the features of Java 8 in detail. I also put a link in here to the Oracle website in there what's new, so you can see some of the other little things that we didn't talk about. We have a very complete set of Java training offerings, which I've listed here, and my hour and 1 minute is over. So I appreciate your coming, and I encourage your questions. Please do feel free to contact me at the email address here, glippa@themisinc.com. Thanks for coming. Have a great day.